Bielkiewicz, and I'm group number 1 reporter doing the experiment number 5, gas turbine jet engine. Introduction, basically just analyzing the jet engine, the pressure, temperature, and energy work at different points in the system, and the practical applications are a jet engine like a gas turbine as being produced here. A little bit of background, I'm going to find the pressure, work, energy at different points. And without getting too detailed, you got the inlet, you've got your compressor, turbine 1, turbine 2, and your generator, and it goes out through the back. So the general procedure, we checked the oil, made sure it was filled up. We actually had to put a little bit of oil, I believe. Made sure the setup was correct. We added kerosene. We had to add a lot of kerosene to the fuel, actually. We increased the pressure to at least 120 psi. We hooked up the air compressor to do that, and then ran the experiment. And just a general note, we ran the experiment, but the MyDAT computer wouldn't work, so I was sent the data from Philip from a previous experiment. Fuel data, we use kerosene, as I previously mentioned. Its energy content per volume is 35 megajoules per liter, 796 kilogram per meter cube density, which is a little bit less than water, so it's pretty comparable to water. Barometric pressure, 101 kilopascals, which is just the atmospheric pressure outside. So the first one is compressor inlet versus outlet versus time. So as you can see, the inlet stayed pretty constant, and then the outlet pressure increased, as shown, because right when it went in that compressor, when it was coming out, the pressure shot up, and then the temperature, the inlet was pretty consistent, and then it had a spike on the outlet whenever it started going through the system. Turbine 1, the inlet coming out of the compressor was generally higher and had more peaks than the outlet, and then for the temperature, the inlet was pretty consistent, and the outlet had a few more sharp peaks going down in temperature. Turbine 2, the inlet was higher in pressure than the outlet, and then for the temperature, the inlet was also higher than the outlet. So going back to turbine 1, they kind of flip-flop. The inlet's higher than the outlet for the pressure, turbine 1, and then for turbine 2 it flips. Fuel flow versus time, it averaged around 2 or 2.5 liters per hour of fuel flow versus time. It had a few peaks at around 3.5 liters per hour, about a third of the way through the experiment, which is whenever the RPM was turned up to the highest, is why that's a little bit higher. And that's shown again through the engine RPM versus time. And of note here, it reaches about 60,000 RPM for a jet engine, and a car obviously is about 2,000 RPM, so significantly higher. Generator RPM versus time, and the next plots are going to show this same curve because they're analyzing the actual generator. So there are 3 peaks around halfway through the experiment toward the end, because that's whenever it makes no sense. And then voltage, same trend. It had a few peaks, and it peaked at around 10 volts 3 times. Same thing with current, peaked at around 70 amperes 3 times. Same thing with power, peaked at around 1200 watts 3 times. And then excitation, I didn't have to include this one, but there's only one more parameter to put in there, so I put it in there and measured in VDC. So my analysis point, you pick a point where the engine RPM is near its maximum, and this is around 59,000 RPM. And the data was taken, sent to me on March 29th at 5:55, barometric pressure, and then the compressor inlet was much lower than the exit pressure. Turbine 1 inlet was much greater than the exit pressure. Turbine 2 inlet pressure greater than the exit pressure. The fuel flow at that max was 3.35 liters per hour. As seen from the graph, the average was about 2.5. The max is about 3.5, so it makes sense. The compressor inlet temperature lower than the exit. Turbine 1, inlet temperature greater than the exit. 2, greater than the exit. Voltage and current. So you take your enthalpy at the analysis point from the air table, so you have to find your CP and then T1 minus T2 of the specific point used, and I'm going to do that next slide, but these are your enthalpies. And then the specific work by the compressor, either CP T2 minus T1 or H2 minus H1 is the equation used, it ends up being the same thing. So work by the compressor is 56 kilojoules. Specific energy added during combustion, 777 kilojoules per kilogram, which is a good bit because it's the highest number here because combustion is whenever you're having the most energy that's added and used. For the turbine, 270 kilojoules a kilogram. Turbine cycle, 555. The efficiency I found is the work divided by the heat input, which is around 50%. And lastly, the specific work of the free turbine, 400 kilojoules per kilogram. So these are the data taken from that experiment. It kind of goes hand in hand with what we thought it would be as well. Done.